Alright, so there was a request to look at problems 3 and 4 of this homework set with the note that there seems to be a substitution that your peer who requested it is missing. So I'm not going to work through the entire integral for these problems or really giving the details of setting it up. I'm just going to go over the substitution and kind of the general shape so that you all can still practice that other part, since it's not what the question was about. So for problem 3, we've got this integral from 0 to 3 in x, 0 to root 9 minus x squared in y, and we're integrating cosine of x squared plus y squared. So when I see x squared plus y squared, I kind of know that I'm thinking about circles, thinking about polar coordinates. If I hadn't been told in the problem that I should be using polar coordinates, my hint that I should use polar coordinates would have been that I see this x squared plus y squared, which I know is going to become r squared, and that's a little easier to deal with. So the shape that I'm looking at is bounded in this part of the plane, x, y. X can go from 0 to 3, and then my upper bound for y is y equal root 9 minus x squared, or y squared is 9 minus x squared, so x squared plus y squared is 9, which is 3 squared. So that tells me that this upper bound for y is going to be part of a circle with radius 3. And then the lower bound is y equals 0. And then we can see that my bounds 0 to 3 for x just mean I'm filling in this whole quarter of a circle that I've drawn here. So that's the region over which I'm trying to integrate. I'm going to set it up in polar coordinates, so if you want to do that, just identify the radius and theta that we want to use to fill in this area right here. When I do that, I'm going to get whatever I think the radius is, whatever I think the theta is, I would put those numbers there. And then my dy dx becomes r dr d theta. Don't forget the r. That is usually what causes problems in this section. And then one of the substitutions that I'm always allowed to use is that x squared plus y squared goes to r squared. So I would actually be integrating cosine of r squared instead of cosine x squared plus y squared. And I would just be putting some numbers on these bounds that I'm going to let you all have the fun of figuring out for yourselves. And then the tricky substitution here is I just have to make sure I include that r in my dA term. And then I can do a u sub. U is r squared. So du is 2r dr. Or I can replace r dr with du over 2. And then you're just going to have an integral like cosine of u du. And if we just take it piece by piece, it should be a pretty straightforward integral to solve. So that's the first one. I guess I'll mention, remember that to fill in those numbers I didn't tell you, our theta is going to be the theta that takes me sweeping through the circle in the direction I just drew, and the r is going to be from the origin out to the edge of this circle to fill that entire area. And those should just be numbers, so we shouldn't get anything else weird happening in this problem. For problem 4, which is a little bit more complicated, it says there may be something wrong. There's nothing wrong, don't worry. I'm not going to draw that shape, but it's bounded between a circle and a cardioid. I am going to write down that we're told we're going from radius 3 on the inside to radius 3 times 1 plus cosine theta on the outside. Okay. I'm going to sketch that picture just a little bit. It's kind of like this crescent shape. just so that I can point to the parts. So here's my radius 3 on the inside. Here's my radius 3 times 1 plus cosine theta on the outside. And so that's how I get my bounds for r. And then my bounds for theta are just going to be what I need to cover this whole area. And then I think I'm just finding the area, so there's nothing. Yeah, okay. I'm setting up a double integral in polar coordinates to find an area, so I don't have to put anything inside my integral. It's just going to be dA. And remember, for our polar coordinates, that's going to be r dr d theta. And then I have to pick what direction I do my integral in. It could be d theta dr instead. But remember, I'm given r in terms of theta, so I want that to be my inner integral. So I do prefer the order that I wrote down originally. And I can go ahead and put those in right away. I'm told that the inner radius is 3 and the outer radius is 3 times 1 plus cosine theta. If I wasn't told that, I could look at this picture and sort of be able to tell that the inner radius is the circle with radius 3. And if I knew what a cardioid was, I would be able to tell that's the outer radius, but that's not something that you would need to know on an exam, just basic shapes. And then for my theta, I'm going to be setting up the angle that I have to sweep through like I drew with this arrow and this arrow. And so that's just going to be like minus pi over 2, pi over 2. If you don't like negative angles, you can sweep it like all the way around and start from 3 pi over 2. But when things are symmetrical like this, it's nice to do it that way. And so far I haven't seen where the weird substitution comes in, so I'm going to go ahead and start integrating and actually work through more of this than I thought in order to make sure I see the issue that your peer was having. So my first integral is with respect to r. Oh, I guess one way this could have gone wrong is if you had chosen to integrate with respect to theta first, you would run into the problem that you can't deal with it on the outer bounds. So do make sure you're starting with r on the inside. But if I'm just integrating r, it's going to become 1/2 r squared evaluated from 3 to 3 times 1 plus cosine theta d theta. So that's going to be 1/2 times, man, that's going to be unpleasant, 9 times, do I want to multiply that out or not? Let's think about it. I guess I'm going to multiply it out. 1 plus 2 cosine theta plus cosine squared theta minus 9 d theta. I'm going to pull that 9 out front, I guess, with my 1/2. So I'm just worrying about integrating this. These two cancel out, so I just have left over inside my 2 cosine theta plus cosine squared theta d theta. Let me write that 9 over 2 a little bit better. So integrating cosine should be no problem. I figure it's this cosine squared that presented the problem to us. So for that, I'm gonna need a trig identity. Okay. 0 plus cosine 2 theta. Okay. So from this identity right here, cosine x times cosine y, cosine squared is just when x and y are the same thing, so it's going to be 1/2 cosine 0 plus cosine 2 of my angle. So for us, cosine 0 is 1, so it's just going to be cosine 2 theta. And then you could go ahead and integrate that, no problem. Using like just a u sub on the 2 theta. So I would just substitute in that quantity here. 1/2 plus cosine 2 theta over 2 d theta. And we can do the sort of 3-part separate. Integrate this with respect to theta, no problem. Integrate this with respect to theta, no problem. And then just do this one with a u sub on 2. Sort of u equals 2 theta. So du is 2 theta d theta, or theta d theta becomes du over 2. And then you should be able to finish out this problem. So thanks for the request for today, and good luck, everyone.